Maarten Bonnema is Professor of Systems Engineering at the University of Twente. After spending several years at ASML, he decided to move to academia to take a deeper look at the principles behind systems engineering. Over the course of his career, Maarten worked with many companies. Currently, he is exploring the origins of the Dutch approach to systems engineering and what makes it distinctive. I sat down with him to talk about his passion for the field and to ask how systems engineering can be applied most effective. Maarten Bonnema, welcome at Bits&Chips, and thanks for having me here in Twente.
Welcome. Very nice to have you here.
Let's start and flash back to the beginning of your career. You studied electrical engineering with a specialty or focus in micromechanical systems, which was a nice topic here at the university. And then you started in industry, isn't it? You started at ASML.
Well, in between there is the engineering doctorate that I did in Delft. Okay. After graduating here, I went to Delft for a little over 2 years to do engineering doctorate in technical systems, which was, for a very large extent, I learned the fundamentals of mechanical engineering and some extra mechatronic design.
And then you ended up at a still quite small company with the name of ASML.
It was at the end of my engineering doctorate and I was looking for jobs. And at that time you had the paper advertisements in the Netherlands, the intermediaire. And I scanned it and at a certain point in time I saw the ASML advertisement for, well, I think it was quite a broad advertisement, but there was one specific also for systems, the system group. And I sent quite a generic application, was invited for interviews, talked to many people already in the interview phase. Was very interesting. And I was hired.
But at that time you didn't actually know what system engineering was?
No. The term systems engineering, maybe I should have, I had heard of it, I don't know. But I became part of the system group, which at that time was a group of individuals that were officially, let's say, in the organizational structure part of other groups. I was allocated to the electrical layout group, but they were sitting together to make sure that new systems were composed in a good way. So they were responsible for what is called the SPS and the SDS, so System Performance Specification and System Design Specification.
How did you experience ASML in the very beginning? What did you see?
So this systems group, it was a group of great individuals, very, very smart people, very interesting interaction between the people. The big advantage, if I would compare the job of a systems engineer then with that of now, is the whole development organization was on the order of, I think, 150 people. So you could know everybody. Yeah. Not detailed, but at least when there was a name you would know where you had to go to have a chat. Yeah. That's now completely impossible.
What were the main things that caught your attention? Were there any surprises?
Well, I was then very young and maybe I didn't have a clear vision of what I should expect. Making the switch to industry or starting in industry was also a great new adventure. But what I loved is the fact that you are working on the whole system. You look at the entire system, not focusing on just one element, which can be a challenge and it can be very rewarding to work on that. Let me be clear about that. To me, the interesting thing is to have the big picture, try to see the whole and understand where the crucial elements are. The bits and pieces that make or break the overall system performance.
Yeah, but you explained that you were working on the electrical layout.
No, I was allocated to the group of electrical layout. Okay. And one of my early responsibilities was to document, the controller architecture of the machine. So I had to talk with many people. It was not directly related to electrical layout because that had to do with grounding concepts and rack concepts, etc. I was involved there a little bit, but to be honest, I'm not so very good at that.
What were the main things that you learned at ASML that you actually would be using during your whole career?
That is really the systems approach. thinking about the system, putting the system central, not the elements, not the parts. The focus also on customer value. What is it that the customer really needs? So that goes beyond what you write down, what the requirements are.
How did you experience that in your job at ASML? How did...
So when we were working on the new, the 300mm wafer scanner, we had discussions, and my great example, Eric Loopstra, was very good at it, and we had discussions in front of a whiteboard. What is it that the customer really needs? So, and then it's not simply more wafers per hour. It is not making the wafer scanner cheaper or whatever. It is about how many good dies do you get out of the machine in a given time frame. And so that goes beyond speed, because it also includes delivering quality, making sure the imaging is good, the overlay is good, etc. Reliability, knowing when the system goes down, is not that bad if you know it quite far in advance and you can plan it. But if the machine suddenly breaks down, you have a big problem.
Would you say that customer needs and going after the customer needs, that was already a central point in the whole development organization of ASML?
Let me answer like this. There were quite a few people who understood that. I'm not sure that it was really, let's say, ingrained in everybody in the development organization. I don't know.
But you gave an example, like Eric Loopstra really pointed questions to that topic, especially that topic.
Exactly. And there were more people, of course.
Yeah. So actually, after your career at ASML, that's about 4 or 5 years, you decided to go to academics. Why was that?
The job of being a systems engineer is fantastic. Designing such a complex new machine, great. But I also experienced in myself some kind of unrest about not sitting back every now and then and thinking, how can we do things better? And well, it was just an opportunity to see an advertisement, and I just applied. Yeah. And well, I hadn't decided I'm going to leave ASML, but I was just looking around, and well, there was a good click with the people around here.
The ASML organization is actually in such a big hurry to get to the next node. Actually, in such an organization, you're not able to sit back.
Particularly at that time, but I believe it is still something they struggle with. It's not the main focus. And then the question is, do you allow a few people to do that anyways? And do you support it? Well, at that time, I had the idea, no. And then the opportunity came to go to academia. Well, there you sit back, and not because you have nothing to do, because it is, I would say, a very busy job, but it is about thinking, how can we do things better? When I went to the academia, I felt also the missing part of just designing a great new machine. Yeah. That's also something that in the first years really made me a little bit uneasy. I wanted to design new stuff.
So how did you find a solution for that?
That was a challenge, but I've had a few opportunities where I could get involved with companies. Either through research projects, where so Daniel Borges, my first PhD student, he was embedded in the Philips organization, and I thought along with him, was very much involved too. Of course, I had no responsibility in that organization, but felt connected. And I was also, that was that was before finalizing my PhD, I got in contact with Mappa Lithography. Mm-hmm. They had a very interesting approach to imaging, but the big question is, how do we build a machine around it? And I talked to them whether I could contribute, and at a certain point in time they hired Demcom here. At that time they were located in Oldenzaal, Mappa Lithography in Delft, and they called me, could you be some kind of intermediate for us? And I said yes. And at that time, so I was working 1 or 2 days a week for mapper lithography.
Yeah. What do you mean intermediate between Demcon and mapper, or
Yes.
Intermediate for?
Yes, between Demcon and mapper lithography. So 1 week I would go to Delft, and the other week I was in Oldenzaal.
Yeah. So then you advised actually a quite small organization starting up in lithography with electrons.
Yes.
What did you see there? How was mapper different from ASML, or was it just the same?
No. The approach was completely different. I would say ASML were machine builders, and mapper lithography were physicists. And that gives quite a different flavor. Physicists, they also challenge everything that you, well, if you take experience on how stiff something should be, they challenge that. And they had also a very strong approach. We do the math, and the math is immediately input to the machine code.
So like the stability of the machine, it's not a given that you should increase the mask to get more stability, for instance.
No, but also if it is about frame stability, you would use some kind of generic formulas. In Dutch we call them the vergeetmenietjes. The physicists challenge that. Is it accurate enough? Is it correct? Etc. So go back to the first principles. Whereas the mechanical engineer, he knows, okay, if I have a beam this long, it has to be this fat to get this stiffness. More of it's the difference between going back to the fundamentals, the first principles, or taking standards, taking let's say experience formulas and use that. The mechanical engineer often works with dimensionless numbers, where that combines a lot of things, and you know it has to be between 3 and 5. And the physicist challenges that.
So I can imagine that has advantages, but also some drawbacks.
So you have to be, in the mapper culture, you have to be way more thorough, but it also goes slower, because you have to go back to the principles. And that was an interesting combination. So when the beginning was really a group of physicists, they were struggling to build a machine. Because building a machine means that you have to, yes, you have to understand the physics, but you have to make it concrete, you have to make it tangible, you have to implement it in a usable structure that is not only, let's say, good from a functioning perspective, but also you can manufacture it. You can ship it, you can maintain it.
So in that way you could keep in touch with what was going on in industry.
First of all, I could indeed stay in touch with industry. I, well, for my personal satisfaction, help in building the machine. But at that time I was also with my PhD research in a stage where I wanted to try it out in practice. So I did that at the same time. So if you look up my thesis, there will be something about mapper lithography.
Would you say that in the beginning of your career, system engineering as a research topic wasn't taken very seriously in the academic world?
People consider it a strange area of academic research. And that has also a bit to do with, a lot of people say, when you explain the principles of systems engineering, they say, oh, that is just common sense. And I agree to it for a very large extent. The problem is people forget that they have a common sense, and everybody has his own common sense, and how do you align on that? And then it becomes very interesting. And then it also becomes more than just engineering, it is also very much about interpersonal relationship, communication, being able to do that. And that became over time more an important aspect.
Why is system engineering, in your view, a research, can be research, and is it a research topic?
Let's say it is not that difficult to develop some kind of tool or method that from an academic perspective is very nice, has a sound underpinning. You can write a good journal paper about it. That's all very well doable. The challenge is to get it also adopted in industry.
It has to be usable.
It has, it has to be used. And I think when you when you're learning systems engineering, to get to the basic principles of systems engineering doesn't take that much time. It's not very difficult. But it starts paying off when you are applying it and you see, oh, wait a second. I do not only have to watch the interfaces, but I also have to explain it to others why this interface matters. So it helps to have some kind of format that many people can easily understand. And I think that is a big challenge for doing systems engineering research. This is also what model-based systems engineering is facing. I would say from an academic perspective, it is very clear that model-based systems engineering is the way to go forward. Mm-hmm. Why are companies struggling so much to do it? Yeah. Because it doesn't connect, it's not directly compatible with the normal way of working. Yeah. And I would even say it is a bit like a missionary person going to some country in the world to tell the gospel, but then expecting first that the people there learn the language of the missionary man. That's the wrong way around. Yeah. It should be the other way around. You first learn as a missionary the language of the people where you are going, yeah, and then you start preaching the gospel.
Let's start with model-based system engineering first. What is, in your view, model-based system engineering? What's your definition?
Then I have to put it next to the, let's say, the classical approach, document-based, paper-based systems engineering, where you use a lot of models to explore what's going on, how do things relate, etc. But the truth, the reference, the baseline is in documents and pictures. Model-based systems engineering is you still use models, but the truth is there. And you require a way to manage the models in a consistent way. And that is, in the ways that I've seen for model-based systems engineering, a tool set that helps you to manipulate the models, query the models, get the information out that you need.
So you make a one common view?
No, not one common view. You make one comprehensive and consistent set of models and interlinked models where you can, from different viewpoints, get some information.
You get a common truth.
You get a clear reference truth.
Yeah. And tooling helps you with that?
I think tooling is essential.
Yeah, it's essential, but what is the danger of the tooling?
The danger of the tooling is that the systems engineer becomes a tool operator. Yeah. And that is when people want to teach systems engineering by starting with model-based systems engineering, I get very uneasy. Because then you more or less educate people to operate the model-based systems engineering tools, but you forget about the underlying principles. Principles like watch the interfaces, communicate with very diverse people, be able to make a very simple picture of a very complex machine, and all these type of things. Think in systems. Crucial.
Somebody who wants to bring this model-based system engineering gospel to a new industry or a new tribe, yeah, they should actually first learn the language of the tribe.
Exactly. So we as systems engineers, if we want to preach the gospel of the MBSE, yeah, we have to speak that in a language that is very close to what the mechanical engineers, the electrical engineers, the software engineers, the marketeers understand.
And is that actually the solution to get model-based system engineering in the industry?
I don't know whether it is the solution, but I would say it is an essential step to make. And what I see in the research community, there are great things happening in the model-based systems engineering world, but it remains in that world. And when you talk to companies, they say, how do I have to do that? Yeah. Because they often feel, I just have to change my complete way of working. I have to re-educate people to be able to deal with SysML models or other type of models, instead of building on their expertise in handling CAD systems or handling electronic simulation packages.
If you take the decision to approach model-based system engineering and adapt model-based system in your industry or in your company, then it takes years before you really are able to do it in a model-based system engineering way, isn't it?
Yes, and that has also a lot to do with, let's say, history. Because in the things that we do in the Netherlands in complex system design, it is in many cases step-by-step development. We still build on a lot of knowledge and a lot of information that is documented. If we want to make a big step to model-based systems engineering, you more or less have to translate all that information into the model-based world. Yeah. And that is a big difference with, let's say, defense projects in the US that start from scratch. And you can say, well, from day one we are using model-based systems engineering. You do not build so much on let's say, the documentation of old projects, because you're starting something completely new.
So there's a big legacy problem with in companies that already have a history of in a product.
Exactly.
And in defense, you say you build a new tank or a new airplane, and you start from scratch building.
In the military, huh? Yeah. So if you look at commercial aircraft, for instance, you also see this development, but they manage to do model-based systems engineering, I think, a little bit better than the high-tech industry here.
Yeah, at least Airbus, I guess, is quite good in making trustworthy airplanes that don't fall out of the sky. Huh?
Yeah. So, but I'm not connected enough to that industry to say how well they are doing on model-based systems engineering.
What you just told is actually the big problem. It's the legacy problem. You have a lot of documentation around the product and the history of development, and you all have to get that information, or that, well, it's quite valuable information, into the new way of working. It's not only a model, it's a new way of working, isn't it?
Plus the fact that you require from the people, let's say not the systems engineers, but all the other people that have to reference systems engineering knowledge, you ask from them that they are able to understand the model-based information. And that is the example of the missionary. Why would they dive into a new tooling? Why would they learn SysML? They are very good at their job with the languages they have in place. So I think we as systems engineers have to make that translation.
Yeah, and where do we end up? Is the advice to start using like a new tool or a new language like SysML, or can you work with your old way of defining systems?
That is exactly an area of research, and we are starting now a new project. We have developed, the Daniel Borges that I mentioned earlier, developed the A3 architecture overviews, which is a very nice format to communicate a systems architecture. But it's a picture. It's a picture. It is an A3 piece of paper that shows how a system looks like and how the architecture is composed. But it's not a model in that sense that you can query with all kinds of tools. So what we are, the project that we are starting is, can we make I call it a file format, maybe it's not the right wording, but that's up to the PhD to research that, that includes, let's say, the visual information that you see on an A3AO, but also includes the logical information, the model information that tells why is the first function and not the third function. Yeah. And if we are able to combine that into one file, you can and look at it and talk about it with people who don't have a background in model-based systems engineering, but you can also query it from a model-based systems engineering tooling set.
Yeah, so we actually have the tool to have an overview which is actually very simple.
Exactly.
And you have the possibility to get into detail.
Exactly. So that is a research project that we are starting, and let's see what it brings. And if we have that in place, then we could also start using AI to maybe mine existing legacy documents, translate that to the logical information, throw it into this format, and you have also the pictures that are easily communicated. Yeah. But that's a vision. That's for the future.
You mentioned that it's a danger for engineers to become a tool pilot. And why is it a danger?
One of the good tools of a systems engineer is the coffee cup. Just walking around with a cup of coffee and talking to engineers, listening what they struggle with, listening whether let's say the system concept is clear to them. Mm-hmm. You cannot replace that with a tool. You cannot replace that with a chat feed or whatever. You have to listen to the people, understand what they are saying, translate, let's say, some detailed information into what does it mean for the system, or the other way around. And if you think that you can do that sitting behind a workstation, you miss something essential. If model-based systems engineering leads to people doing their systems engineering work sitting behind their workstation, this whole aspect of interaction, communication is lost.
A technical oriented person naturally are driven to tooling and numbers and...
Yes, but a systems engineer should look beyond that.
Yes.
And that's why it is so important to step out of that. The second thing why I would be hesitant when you become a tool operator is then you use your brain mainly to manipulate models. Mm-hmm. Whereas you should use your brain as a systems engineer to see the system concept, the system level implications, the customer, not only the customer requirements, but the customer needs.
Mm-hmm. And you only see that by talking to customers, to your colleagues, to other technicians?
Yes.
Yeah. So actually then this whole idea of the product is actually in everybody's brain.
That should be. Yeah. Yeah. And the question is, how do we make that happen? Well, that's why I love to work on easy solutions.
Because if you have a product development and if you have a model or you have something on the paper or something digital, everybody will have their own story about what they're seeing there.
Exactly, exactly. And just as an example, when I worked at ASML, I also worked on the overlay budget. Mm-hmm. And at that time, when I started working on it, it was a very complex Excel sheet maintained by one or two people. To produce chips, you illuminate a picture on a wafer, and in fact on just a part of a wafer, and then that picture is developed and all things happen to the wafer. Then it comes back into the machine and a new picture is built. Yeah. And the accuracy with which you can put the next picture on top of the previous one, yeah, that's called overlay. And the budget is, in fact, we have a certain number, and I don't know, at that time we had like 60 or 80 nanometers total overlay budget. Now the people at ASML get a big laugh, because at this time it is a fraction of that. Yeah. And you divide the total amount over all contributors. Yeah. And that means something happens in the processing, something happens in the loading and unloading, something happens in measuring. So how to keep track of that, there was a budget, the overlay budget, and as I said, a very complex Excel sheet. And that also had as a consequence that people said, I get for my stage or for my sensor or for my subsystem only 1 nanometer, whereas my neighbors get 5 nanometers. Yeah. Why? And I made a picture then in the form of a tree of how the whole budget fits together. Yeah. And that was a representation that I had it with me when I talked to people about it. Mm-hmm. But many people wanted to have it. And after a while, you saw it in different places in the company hanging on the wall. It was, by the way, an A3 sheet of paper, but that was coincidence, I would say. Because now people started to understand why they only had 1 nanometer, whereas others had 5. So it is a lot about communication. One thing, we already talked about it, that how did I stay connected to the practice? Another way that I did was being involved with the solar team Twente. Developing the solar racer. I did that for a couple of years. And then you would have a designer working, let's say, from on the I don't know, subsystem A and another one subsystem B. And I would go to them and ask, hey, make a drawing of your subsystem with the interactions to the rest of the car. And I go to someone else. And if they were neighboring subsystems, I would put 2 pictures next to each other. And in 9 out of 10 cases, the pictures don't match. So you know something will go wrong if you start to build this.
Yeah, yeah. So that was an opportunity for both sides to communicate.
Exactly. And I just helped them a little bit.
Yeah, actually you pointed out that they should communicate more.
Yes, exactly.
Yes, it's a big trap in every company, I guess. That people don't talk and they are focused on their work. And it's so much fun to dive into the details that you don't get to talk to other people.
And that is exactly the point why it makes sense to have systems engineers. Because they should look at the interfaces. And now I have the time to correct a misconception, because I often use the phrase, there are 2 types of systems engineers, those that look at the interfaces and amateurs. It is a quote from Robert Hellingen from PPI. So let me be very clear about that. I use the quote, it does describe the essence of what a systems engineer does. One of the essences, but a very fundamental one. And indeed, what you said is absolutely correct. A mechanical engineer wants to just make a very nice frame, and it is not in their nature to think about the interactions with other parts of the system. And the systems engineer is fundamentally responsible for making a well-balanced, well-composed, functioning overall system.
Your inaugural speech was about
complex tasks, simple tools.
Why did that catch your attention while you were there in Australia?
The reason for being in Australia was that the students from industrial design engineering were going on a study tour, and they asked me to join them as a supervisor. Mm-hmm. And I have a weak spot for Australia, so I joined them. Very nice. And the next part of that travel was to write also the inaugural lecture. So I was looking for a good starting point. Being inside the pillar of the Sydney Harbour Bridge, seeing that phrase, complex tasks, simple tools, it struck me, this is a great title, and it is also a great theme. And the more I thought about it, the more that started to live. Because as a systems engineer, you have to do a lot of complex jobs. And we love to make things more complicated. That's, I would say, for many technical people, but also other people, the natural approach. There is a problem, we add something to compensate or deal with that problem, etc. And we make things bigger and bigger and bigger and complex and complex. But the Sydney Harbour Bridge in itself is a great accomplishment. Also showing a lot of vision about where are we going, because it was in the 1930s it was designed, and it's huge. Also the amount of traffic that it can carry. I think there are now 8 traffic lanes. Think of it, in the 1930s, that you would already put 8 traffic lanes. How many cars would there be in the entire continent of Australia? Not that many. But they thought about that. There was a vision. And that is also what I think a systems engineer should do. But now back to complex tasks, simple tools. Yeah. So we should go the other way. There is this famous quote by Albert Einstein. Any intelligent fool can make things bigger and more complex, but it takes a lot of courage and a bit of genius to go in the other direction. And I believe we should go in the other direction. Translate it back to the essence. I mentioned the A3 architecture overviews. That's exactly an underlying principle there. Do not fill thick documents with the architecture description, but describe what you have to tell on an A3 sheet of paper. And if it doesn't fit on the A3 AO, then don't reduce the font size, but dive deeper and try to understand how you can make the message clearer and more compact.
And if you take complex tasks, it's not about complexity, but it's about tasks that are the job that is quite complex, and you have to go to simple tools to be able to do system engineering.
Exactly, because if you would also use complex tools to do complex tasks, you make things very complex.
Yeah, so actually you need tools to make things more simple.
The tools itself should be simple to support you in the complex tasks that you have to do.
So then if you look at the person that has to do this system engineering job, what should be his traits or her traits to do it?
I would say the discerning trait for a systems engineer, there are many things that a systems engineer should be able to do, but handle uncertainty is fundamental.
But let's start with the basis.
Yeah.
He or her should have a technical background, or not?
Most systems engineers that I know have a technical background, but I do believe that, let's say, some artistic people and some social science people could also be a systems engineer, but they do have to, let's say, learn some of the engineering language. It's not strange that a part of the systems engineer job is systems architecting, that we use the word architect there. Whereas architect it's a little bit between technical and arts. And I believe that the job of an architect, a building architect, has a lot of parallels with the systems architect. And funnily enough, I recently read the full article by Henrik Bode from 1967, long time ago, on system engineering. And he compares indeed the job of a system engineer to an architect. But by the way, if you have a little bit of time to read that article, because it is still very, very, very valid today. The message is what is systems engineering about, and it is a lot about the system view, it is about the interfaces. Well, he sums, I think, 6 or 7 things, and it's all very, very relevant.
What is important to keep in mind to become a system engineer? How do you become a system engineer if you're interested in that?
I could answer this along 2 lines. One is, how do you become a system engineer? And the other one is, what does it take to become a system engineer? Which one do you prefer?
What does it take?
What does it take? So what are the things that you should have or learn? First of all, fundamental, being able to deal with uncertainty. And why do I say that as fundamental? Of all the things that a systems engineer should be able to do and be able to handle, this one is, I think, the one that is most difficult to learn. This is something that is, either you are comfortable with it or you're not comfortable with it.
Yeah. Maybe it's a very attractive job because you're a leader of a team, but you have to look yourself in the mirror. Exactly. And if you're not comfortable with uncertainty,
then don't do it. Then you can better become a project manager, which has some parallels, but has a completely different responsibility. And I think there it is less important to be able to handle uncertainty, but I'm not an expert in project management. So the other thing is curiosity. You have to dive into new technology all the time, new aspects. You probably have a home discipline, but you should also be curious enough to dive into a different discipline. Yeah. and communication, being able to communicate.
If you talk about curiosity, it means that if you end up in a new design project and you have to deal with a new submodule or a new technology, you really have to make sure that you know enough of that field to be able to handle the total system, or at least to communicate about it.
And to such an extent that you are taken seriously. Because if you act as a system engineer by the person who talks about everything but is nowhere really well rooted, you're not taken seriously. So you have to make sure that you know the essentials, you know what is relevant in this discipline, have to know some of the language that they use, and be able to communicate with people, and have a bit of scar tissue maybe in that field helps to be taken seriously.
Yeah. And if you talk about communication, a lot of technicians really are confident in their field and are sure about a certain solution, but they feel very uncomfortable when they have to speak up in a team. Mm-hmm. And maybe as a system engineer, you have to help those people in your team that they make themselves heard.
Yes. And also be able to translate the message from, let's say, an electrical engineer to what it means for the software engineer. Or to the mechanical engineer.
So that means you have to have quite some experience in system development.
What I also often say is, as a systems engineer, you have no power, but you have influence. So you cannot force a decision in many cases. There are some exceptions, of course. But it should be the case that when you speak, people are listening carefully because they know there is something important being said here. Mm-hmm. And that's what I mean with influence. And then probably someone else makes the final decision, is responsible for the final decision.
Gerrit Mullers says that if there is in the development team or in a small company, for instance, if there is not a job as a system architect or a system engineer defined, then the one who goes from room to room and talks a lot to people, that's probably the system engineer or the system architect.
Exactly. Yes, I absolutely agree.
If you look at the Dutch approach to system engineering or the Dutch way of engineering systems, is there something to say about our skills and how we differ from other cultures or other countries? What are our strengths?
Let me go back to this chapter in the report by Henrik Bode that I mentioned before. Yeah. He comes from a defense background. Mm-hmm. INCOSI, the International Council on Systems Engineering, has a very strong background in defense and aerospace. Yeah. And what you see there is it is a lot about being very thorough, identifying risks very early, making sure that when you send a satellite up into space, that it works. If you look at the type of successful systems that we produce here in the Netherlands, it's different. It is, yes, you identify the risks, but sometimes you go head on with them. Mm-hmm. And it is much more about making sure you put out the system into the market early than it is about it never has a problem. And I think that means that we are using the same principles, the same tools from a systems engineering perspective as the ones that are described by INCOSI, yeah. But we use them a little bit differently. Or NASA, exactly. And we use them a little bit differently. And what makes us Dutch apparently very good at it? I think the communication and organization culture play an important role here. Mm-hmm. In the sense that hierarchy in the organization is less restrictive. Anyone can challenge the boss if he or she has a good argumentation. And I think that helps to drive down to the essential parts of your system design. And helps also to make the right fundamental choices for your design. On the other hand, apparently we dare to take these risks. We are not so risk adverse. We dare to take them. We make sure that we have the essential information, but we don't care whether it is the top-notch engineers who tells it or someone who just started but has a good argumentation for it. Yeah. And that is maybe where it boils down why we are good at it in the Netherlands. And we talk a lot. That's Dutch. We talk a lot, meaning we look at the problem from multiple perspectives. Yeah. And then at a certain point in time we dare to choose. Yeah. And I think that makes the Dutch systems approach strong. Yeah. There is this next-gen high-tech project. Mm-hmm. It is also about getting a good fundamental view on why we are so good at it. Mm-hmm. I gave a very condensed view from my perspective. That doesn't mean that it's the truth. And there we involve multiple companies and we make sure that we share how they do it and why it works. And then it could be that company A learns from company B, yeah, which is good. We also want to write it down. Writing it down sounds very static, but at least grab it in such a way that it can also be transferred to others and very much create or support educational programs. Yeah. So that if someone learns the systems engineering approach here in Twente, but they go to Delft, that there is at least some commonality. Yeah, yeah. And that when a company hires someone who has been educated in systems engineering, that they know what they get independent of where they studied it. We are working on a reference framework so that we understand what we are talking about. And there is also the ambition to deliver some curricula. And not as this is the only way to do it, yeah, but as a reference. Hey, if you want to set up a program, if you want to set up a master course, if you want to set up a professional training, here is a reference. Yeah, yeah. And use these terms and make sure that you include at least these elements. Yeah, yeah.
What is already known and usable in your view?
This is disconnected from this research project. Yeah. What I think is essential is that you learn about what is the systems engineering process, what are tools that you make use of, and what is system thinking. Because system thinking is fundamental to be a system engineer. And then it is all bound together by communication. Also create more visibility of the educational path towards a systems engineer, where I do not believe that in a bachelor program you can educate systems engineers. I do believe that in a master program you can prepare people to become a system engineers, but when they are done, they are not systems engineers. So you have to learn still after your master. So trainings on post-master level, or, and I'm a very big fan of that, the engineering doctorate towards becoming a systems engineer. That's also one of the things. And then we create references for that. There are so many people talking about system engineering these days that there is a large need for it, and there is a lot of struggle in how do you become a system engineer.
I think you'd say that there are too few system engineers, but is the potential to have a bigger system engineering community, is it there? Are there enough people who have enough background to make that step to become system engineer?
Yeah, we should be careful.
Not to make everybody a system engineer?
Not to make everybody a systems engineer, because that would be not very effective and efficient. So far, there is still an increasing need for people with a systems engineering profile. I think that if you look at also some research that's being done, that in a development effort, there is in the order of 15% of the effort has to be put in systems tasks. So of all the people who are involved in product development, 15% has at least some affinity with system engineering. That would be good. That doesn't mean that the other 85% should be completely ignorant of system engineering, because it is in many cases the binding element, so then you have to know what it is about. Yeah. So every engineer, I think, should have a basic understanding of what it is. Yeah. And the conclusion can be, it's not for me, it's great. I have no problem at all with it.
Yeah, that 85%, Gerrit Muller says about those 85%, he says, if you're as an engineer, if you're technical capable, but if you can add more communication and be more sociable, that then you improve your engineering capabilities.
I agree, and I'm willing to handle uncertainty. Yeah. I would add to that.
Thank you for the discussion, Maarten, and thank you for having me here in Twente. Thanks for listening to my interview with Maarten Bonnema. If you found this information insightful, make sure you subscribe to the Bits&Chips podcast. By subscribing, you'll be automatically notified when we publish new interviews and upcoming editions. In the coming weeks, we'll publish interviews with Arie de Boef of ASML and Ashok Sridhar of Traxel. Thanks for listening. I hope you'll join us next time.